If there is now these differences, then the brain should make use of it. And the most straightforward way of testing that is to look at a brain. So this is a brain, here's the frontal part, here's the back part. This is a brain of a macaque. And we measured or estimated this R value for each of the different brain areas. The brain areas that you find here blue, that have a relatively low branching parameter, and they're farther away from the critical point. These are the ones that are receiving the visual input. And brain areas that receive input, like the visual input, one could argue that these, in fact, should be far away from the critical point, because they should be, in principle, sensitive to input, but they also should forget the input very quickly so that the next frame, the next information, can go to a clean network again. In contrast, then here, frontal areas and then also the motor output, these might profit from being closer to the critical state, because there they can integrate information from different modalities and over longer time. So seeing that this R value is different across the different brain areas, smaller in the sensory areas, larger in the integration areas, is a hint that indeed that mechanism is being used and has been developed either by evolution or by learning. So we argue that neural networks adapt their collective dynamics and computation to task requirements. Now I would like to tell you how these networks regulate towards or away from a critical point and how they do that in an emergent, self-organized manner. The video that I show here, okay, what you see here is single neurons, and they don't have any connections. And this is now a time-lapse video where these neurons grow their connections. They're growing these connections over the course of a week or two. I'm sure they don't only grow the connections, they also adapt the strength of these connections according to the rules with which probably they also adapt the strength in the real brain. So we assume that the rules of how these connections are formed here in the dish are very similar to those that are also implemented in the brain. And what do we find? So these networks, after about 10 days or 2 weeks, they start showing neural activity. And the neural activity, this is all that we can measure over time, that shows very clear bursts. It's quiet for a while and then it goes off like bang. And the time scale here of 5 seconds means that there is a huge burst of activity every couple of seconds. It means that the entire network is active, it's silent, it's active again, it's silent. Here's a second example where the bursts are a bit more dispersed, but still bursty. And I guess you all agree with me that your brains are not showing such activity. They're not quiet and bursty, but this is something that happens in vitro. So when you put such a neural network into a dish, into a small petri dish. In vivo, if you record activity, it's way more continuous. And that's a long known and very puzzling contradiction. Why do we have a neural network in vitro showing a strong burst and in vivo, in the real brain, showing this more or less continuous activity? We provide an explanation based on homeostatic plasticity. Homeostasis is a control theoretic principle. You can imagine it, forget about the text that's written there, you can imagine it as your regulator of your temperature, so your air condition. If your temperature is too high, then it will cool down the room. If it's too low, it will heat the room so that it reaches a certain temperature. Likewise, homeostatic plasticity maintains a target activity rate for every single neuron. It just wants to make sure that every single neuron fires and is active with a certain level. It's not quiet, it's not overly active, but it has a certain level. And it does it by regulating the excitability or the coupling strength between the neurons. Here's a sketch of that. This should depict a neuron. This should depict all the connections. Here would be the target on the scale. If the neuron is too little active, then it should increase its coupling until it's sufficiently active, and vice versa, just the way I described it. And mathematically, this can be implemented in a very elegant manner. So in a manner that we can tune that at every single neuron. We don't need to know anything about the network activity. So the change of the synaptic strength here, the coupling strength, the change of the coupling strength at every single neuron, that should increase if the neuron is not activated. So there's a small drift upwards. The coupling gets stronger and stronger and stronger with the time. And it decreases stepwise if the neuron itself has been active. And it all happens very slowly so that the network converges to a stationary configuration. And we do that at every single neuron. So the advantage is we only need local information. We don't need the supervisor that tells which neuron to decrease or increase its coupling. We don't need any memorization of spiking activity. They just drift up and decrease when they're active. Drift up, decrease when they're active. And we have, in principle, we can implement different target rates, which makes it more naturalistic. We then put that onto a topology of neurons that we have been growing there with some natural rule. And what do we find? We do find that if the input is very weak here on this side, here's the input depicted. It's 1 in 10,000 neurons, 1 in 10,000 activity pulses is from the outside. Everything else is internally generated. Then the activity over time shows this very strong bursts. And if we then increase the input to about 1% of the activity being external, then we come to this more continuous activity. All of these networks have exactly the same mean activity. It's just that one of them goes strongly bursty and the other ones get more and more continuous. So it is the external input strength that determines whether the system is, surprise, surprise, closer to a critical state or farther and farther away from a critical state. And that also tunes our coding properties. We can now, with the external input, change the coding property of the neural network. These long intrinsic timescales, long active memory, and high variability is a property if we have, in general, very weak input. If we have stronger input, then there's short intrinsic timescales, there's faster forgetting in the network and less variability. So under homeostatic plasticity, the input strength changes the collective dynamics. It becomes a control parameter. It changes the functional recurrence R and hence the abstract computation properties. And that's something we can also make use of in generic tasks. I'll not go into the task, but just mention that in one sentence, it's here, the Kramer paper, we have a neuromorphic chip. They are very difficult to tune, but if we put in this specific rule, then we can tune that homeostatic, we can tune that network such that it will have one or the other computational properties. I want to go into a different direction. So I told you the input strength makes a difference. If you have a completely isolated network, there's hardly any input. We have these neurons in a dish, in this glass dish, they don't receive sensory stimulation, then they develop to the bursts. If they do get input from other brain areas, they would go more continuous. And that is exactly what we find, what matches our experimental data. In vitro, in the dish, the dynamics match. In vivo, we match with the more continuous. And actually, a number of measures indicate that in the real brain, about 1% comes from outside and the other 99% come from inside. And the input strength is now the control parameter for the dynamics. I put in the detour. So if we make use of that for coding, then we can go to this neuromorphic chip. There we have implemented a number of neurons in hardware. That's really RC circuits where the coupling strength is adapted. If you put in that homeostatic rule, then we can tune it from one to the other state. But more importantly, we then train it on a nonlinear task, an with parity task. And this nonlinear task has its maximal performance at different points. If we only want to know if you only want to know a computation on the last 5 bits of inputs, then we want to be farther away from the critical point here to the right. If the computation should be performed on the last 50 or 25 bit of input, then it's better to be closer and closer to the critical point. So there we demonstrated on a chip that setting the working point really has an influence on the task performance. So each task in general in our human brain might have its own optimal working point. I would like to briefly go back here one step because I think because what this clearly predicts is that if we would manage to put this in vitro systems, which are so isolated, if we would manage to give them some input and rescue them from their isolation, then indeed we could have continuous activity. With this, I would like to look back on what we have discussed today. We have discussed the branching, the spreading of activity, and how we can infer that under subsampling. We have looked into collective dynamics in the brain and found that the R value might be very close to 0. The R value typically and generally is 0.98 for human brain, cat, mouse, monkey, many different animals. So that seems to be a universal principle to have an R of 0.98, and that this allows collective dynamics in computation to be tuned to task requirements. And I told you about how homeostasis regulates the dynamics. It is then the input strength that becomes the control parameter of a critical dynamics. So you saw how I go from spreading dynamics to information flow, which we skipped a bit, to learning, and to infogenesis. That's what I'm truly interested in, how these networks self-organize, how they adapt their connections so that meaningful function comes out in the end. The other topic that will be driving in future is the pandemic-infodemic interaction, because this entangled spread of information and disease is not only interesting physics system, but it's also important to understand and also prevent the spread of misinformation in future. And it is very similar in a way to the self-organization in neural networks, because we also have to know how the stabilization, destabilization, how potential bursts arise here. So the goal is here to reach energy efficient AI, if you understand that point, and to facilitate pandemic crisis and preparedness in future. With this, I strongly want to thank this very active and very smart and great research group that we have been, that I had the pleasure to work with in the last years. There's Johannes Zierenberg, who drove forward the infodemic, the homeostasis project. And there is Jonas Dening and Paul, with whom we did a lot of the COVID work, and Jens Wilting, with whom we did the subsampling invariant estimator. He's already at Bosch. Thank you very much for your attention.